hard act to follow. I mean, I'm not going to dazzle you with the visuals, that you've seen before, but, I'm going to talk about, my passion, that is clouds. And clouds are actually the constituent in the atmosphere that affects the radiation balance more than anything else. So clouds interact both with the thermal IR radiation and with the solar radiation. And we want to know how that interaction is going to change in the future so we can make better predictions about future climate. So the way the interaction happens with solar and thermal IR is going to depend on the type of clouds you have, on the properties of the clouds. So before talking about the future and what's going to happen, the first order of business is to see what the current effect of clouds is. So next slide. So we have a fleet of satellites, and what we need to measure is cloud properties, and we also need to measure the radiative fluxes, that come out of cloudy skies. So this is the A train. It has many instruments that measure cloud properties, and it has one instrument that measures radiative fluxes. And my talk is going to be based on measurements of that instrument series. But also, I'm going to show one visual for MODIS. So MODIS, and we have the cloud expert of MODIS there, so refer your questions to him. We retrieve cloud properties from MODIS that helps us also understand what the effect of clouds is on the radiation budget. So next visual. So the source of energy for the Earth is the incoming solar radiation. And it has a very large seasonal variability. And the reason, of course, is that the Earth is tilted. So the tropics receive a lot of insolation, but also the summer hemisphere receives a lot of insolation, much more than the winter hemisphere. So this is our energy source. So energy comes in, and then next visual, then it interacts with clouds. So, this is the picture of the cloudy world, for MODIS for a particular year. So I'm showing you the annual cycle here. So you see there is seasonal variability, but there are places where clouds are kind of semi-permanent almost. And one example is the southern oceans. But also the North Atlantic is very cloudy. And you can see actually a zone in the tropics called ITCZ where you have also a lot of deep convective clouds. In the seasonal variability there, you're going to see actually the cloudiness change over the Southeast Asia and Indian subcontinent because of the monsoons. So looking at this, what percentage of the globe you think is covered by clouds? Would anyone dare a guess? Okay. MODIS tells us about 65%, but MODIS misses some of the thin clouds. So we have more sensitive instruments like Calypso. It's going to tell us about 75% of the world is cloudy, actually. So next visual. So one way to measure the effect of clouds on the solar radiation is to look at the albedo. It's basically the ratio of what is reflected to what is coming in. And you can see in places where you have clouds, you have a high albedo compared to the background. But you also have high albedo where you have bright surfaces. So also you have high albedo where you have snowy surfaces. So you see that this is also changing with season because the angle of solar illumination changes, so the albedo of the clouds changes based on that, but also because cloudiness changes, with season. So places where you have a lot of cloudiness are going to light up, in this visual. And you can see that more over the ocean where you have the dark background. So in general, the albedo is actually larger over the winter hemisphere because of more clouds and low solar illumination. But then if you go to the next visual, you're going to see that the amount of energy reflected is larger in the summer hemisphere. So even if the albedo is lower, the fact that you have more coming in makes what's reflected to space much larger. Now, if we move to a different part of the spectrum, the thermal IR, which is the next visual, we actually going to see, in some sense, the clouds a bit better. So, we're going to mute the effect of the surface. So Sahara was showing bright, in the albedo visualization, but now because it's hot, is going to show as a place where you have high thermal IR radiation. And where you have clouds, you're going to have less thermal IR escaping to space. The reason is that clouds absorb thermal radiation emitted from the atmosphere underneath and from the surface, and remit that, some of it downward and some of it upward. So what you see from space is actually the cold cloud top. So what you see is the emission from cold cloud top. So this ITCZ zone that I talked to you about is actually a zone that you see very clearly in the thermal IR part of the spectrum. So you also have seasonal variability because the temperature changes between winter and summer. So you have solar reflected about, for the planet as a whole, about 30%, about 70% is absorbed. So what happens with that 70% is emitted as IR radiations. Now, if I combine what is reflected and what is absorbed actually and what is emitted back to space, I have, in the next visual, I have the net radiation. And now here, I don't see the clouds really, you know, those cloud features that I showed you before very clearly, okay? I see a big seasonal variation, again, because the amount of energy changes. So where it's red, you have a net energy gain, and where you have blue, you have a net energy loss. So throughout the year, for the planet as a whole, this number is very close to zero. But for particular regions and seasonally, it's going to vary a lot. So in the tropics, overall of the year, you have an energy gain, radiative. That extra energy is going to be transported to the other latitudes through ocean currents and atmospheric circulation. Now, why don't you see the clouds here that clearly as you saw before? The reason is that clouds reduce the amount that you're absorbing, but also reduce the amount that you're emitting to space. So the net effects largely cancel each other to a certain degree. In order to see the effect of clouds, you have to take a difference. What difference do you have to take? Difference between fluxes emitted to space under clear skies and fluxes emitted under cloudy skies. Now you're going to start seeing the clouds again. Next visual. So here's what I call the cloud radiative effect. The impact of the clouds on the total radiation emitted and reflected to space. So the combined effect in the short wave and the long wave. Now look at my color bar here. It's skewed towards negative numbers. The negative range is much higher than the positive range. Positive range is only 40, negative range is minus 150. So what you see here is, at most places, clouds cool the planet. That's what the negative number tells me. The shortwave effect, the effect on solar radiation, overwhelms that on the long-wave radiation. But there is an exception to that. In the winter, when the incoming solar radiation is reduced, then long wave can take over. And that's the reason you actually see some yellow. Even though overall the effect is clearly negative, you see some yellow in the winter hemisphere where you don't have as much incoming solar radiation, so not enough is available to be reflected. So overall, clouds cool the planet, and in terms of numbers, we use units that are watts per meter square. The combined effect over the year, it's a cooling of minus 18 watts per meter square. So you have about 48 negative in the short wave and about 30 positive in the long wave. The net result is minus 18. Now, in the next visual, I'm going to show the combined effect of clouds, but now on the surface. Okay. So you're going to see it looks very similar to the one I showed you before. Again, with the same type of seasonal variability and with a very similar color bar. And the reason is that the value at the surface, the cooling that clouds provide in the surface, the fact that they reduce the solar to the surface more than they enhance the emitted towards the surface in the long wave, is minus 21. So it's only about 3 watts per meter square more than it is as viewed from space, what we call the top of the atmosphere. Now, this is the surface, and now you're going to wonder, how do I know what's happening in the surface? The satellites tell me, you know, what's happening at the top of the atmosphere, how do I know what's happening in the surface? So the answer to that is that we use retrievals of cloud properties from instruments like MODIS I talked about earlier, but also from other instruments. And those cloud properties will insert in radiative transfer codes, and then we'll make a calculation using also the constraints we have from the observations at the top of the atmosphere. So there is a little bit of modeling, quite a bit of modeling actually involved to get those numbers, okay? Now, if I take the difference between what's going on at the top of the atmosphere, which I showed in my previous visual, and the surface, is what I have in the next visual, which is my last one. So here I use a different color bar. And when I take this difference, what I'm showing, or what I'm calculating, is the effects of clouds on the atmosphere, whether it cools the atmosphere or whether it warms the atmosphere. So warm are the red colors, and cool are the blue colors. So you see that in the tropics, where I tend to have more of the high clouds, they warm the atmosphere radiatively. And then when I move to the high latitudes, where I tend to have more low clouds, there's a cooling effect of clouds on the atmosphere. So the net effect, the overall effect is quite small. It's only 3 watts per meter square, according to this series data set, at least, that I used. It's a difference, again, between the TOA effect and the surface effect. So overall, you have a very small number, but if you look at geographical distribution, you have very big contrast, and the end result is a result of a lot of cancellation that happen between different values geographically. So I'm going to conclude with that. The main message is clouds cool the planet. In the future, we want to know whether they're going to cool it more or less. And they cool the surface overall and slightly warm the atmosphere. So are the numbers for current climate, and we try to use a long observation record and modeling to guess what's going to happen in the future with respect to those effects of clouds. Okay, thank you.